Okay, and so here we have the final talk at this year's Midwest Representation Theory Conference, and it's going to be given by Aaron Pollack, and it's on singular modular forms on quaternionic E8.
All right, well, thank you for the introduction. It's a real pleasure to speak here. I just want to begin by thanking the organizers for putting on such a nice conference. Yes, I'm going to talk about singular modular forms on quaternionic E8. So what is the talk about? So I want to talk about the construction of two very nice automorphic forms on quaternionic E8. So these are sort of two of my favorite automorphic forms. Maybe I should begin by apologizing for not talking about supercuspidal representation. So this is a global talk, and in fact, it's sort of about some very degenerate principal series in some sense. But so anyway, some special automorphic forms. So E8-4, that's sort of the group that plays the central role in this talk. So this is a real reductive group of type E8 with a real rank 4. So that's what quaternionic E8 means. And sometimes I'll blur the notation and write E8-4 for a sort of a linear algebraic Q group who's split at all the finite places and at the infinite places, this real Lie group. So the symmetric space associated to E8-4 does not have Hermitian structure, but it still possesses automorphic forms that behave sort of very similarly to classical holomorphic modular forms. So I'm the type of person who sort of very much likes classical holomorphic modular forms, and if you want to study automorphic forms on E8, you can't do that. No real form of E8 has a symmetric space that has a Hermitian structure, but sort of this E8-4 sort of comes as close as possible. So what do I mean by they're sort of similar to classical homomorphic forms? What happens is there's a robust Fourier expansion, and which I'll describe a little bit in a little bit, and these sort of special automorphic forms have robust Fourier expansion. They're called the modular forms. And so it turns out that there's sort of two of these special automorphic forms on E8-4 that one can write down very explicitly. And the main theorem that I want to talk about is that once you take into account this sort of Fourier expansion, these two modular forms have all Fourier coefficients that are rational numbers. Okay. The main result is sort of a generalization or an analog to E8 of a result of Henry Kim that's on E7. So I want to begin by reviewing this result of Henry Kim. So there's a group E7-3. So it's a real group of type E7 that has real rank 3. And so this form of E7 has a symmetric space with Hermitian tube structure. And so I'm going to sort of begin, and so Henry Kim's result has to do with special sort of holomorphic modular forms for this group E7-3. So I'm going to sort of begin by reviewing this a little bit. So let theta denote the octonions with positive definite norm form. So I don't, so maybe some people have sort of ran into the octonions before if they've been working with G2 or something, but let me sort of just review this briefly. So it's an 8-dimensional non-associative R algebra that comes equipped with a quadratic form, which is positive definite, and an R linear conjugation, which I'm denoting by star. So you should think of it sort of as an 8-dimensional analog of a definite quaternion algebra. So a definite quaternion algebra is a 4-dimensional associative R algebra, and this is sort of an 8-dimensional analog. So out of theta, you can define, out of these octonions, you can define what's called the exceptional cubic norm structure. So I've denoted that by J, and so this is the Hermitian 3x3 matrices with elements in this octonion algebra theta. So it's a 27-dimensional real vector space whose elements look like 3x3 matrices with the real numbers along the diagonal. That's these CIs, and on the off diagonal, you have these elements of this octonion algebra theta. Okay, and it's sort of self-conjugate. So you have like an x1 on this sort of off diagonal here, and then an x1 star on in the opposite place. So associated to this J, you can make a tube domain. So this is the elements z equals x plus iy, where x and y are in this exceptional cubic norm structure, and y is positive definite. So there's some notion of positive definiteness on these 3x3 Hermitian matrices with elements in theta. And so this is the symmetric space for E7-3. And it acts on it by sort of generalized exceptional sort of fractional linear transformations. So there's a notion of holomorphic modular forms. So suppose L is a positive integer and F is a holomorphic function on this 2 domain. Then F is a holomorphic modular form of weight L if it's holomorphic moderate growth, and satisfies a functional equation for all gamma and some congruent subgroup of this group E7-3. So this J gamma Z is some factor of automorphy, generalizing your sort of usual CZ plus D. And so one of the main points is that if you work on this group E7-3, these holomorphic modular forms have this very nice Fourier expansion. So if F is one of these holomorphic forms, you can write F of Z as a sum of linear combinations of exponentials. So Z is in this exceptional upper half space. T is an element of some sort of rational lattice in J, and it's positive semi-definite. And so T times Z is, well, there's some pairing on this space J, and you can take this pairing and then exponentiate and then add this all up, and that's the Fourier expansion. So it's supposed to remind you of the very sort of classical Fourier expansion of modular forms. And I can come to Kim's result. So there's a notion of, so first note that J contains the 3x3 symmetric matrices. So here's J again. So if these xi's on the off diagonal are in the real numbers, you just have 3x3 symmetric matrices. So J contains the 3x3 symmetric matrices. And there's a notion of rank that sort of extends the usual notion of rank on a 3x3 symmetric matrix. So it's valued in 0, 1, 2, 3. So the only matrix of rank 0 is the 0 matrix. The rank 3 matrices are the non-degenerate ones, and rank 1, rank 2 are pretty degenerate. So here's Kim's result. There's holomorphic modular forms, which I've called theta Kim 4 and theta Kim 8 on E7-3 with the following properties. So theta Kim 4 is a weight 4 level 1 modular form with integer Fourier coefficients. So all of these AF of T's are integers. And moreover, the Fourier coefficients are 0 unless the rank of T is 0 or 1. And then there's a similar result for a weight 8 modular form. So it's a weight 8, theta Kim 8 is a weight 8 level 1 modular form with Fourier coefficients in the integers, and all its Fourier coefficients are 0 unless the rank is 0, 1, or 2. So in particular, the rank 3 Fourier coefficients, the sort of non-degenerate ones, are 0. And so one says that these modular forms are singular because the Fourier coefficients are supported on the singular matrices. Okay. So there's a notion of modular forms on exceptional groups. So that's what I'm going to discuss for the moment. So what are the groups in question? So you take the split groups G2, spin 8, F4, or there's real forms of E6, E7, and E8 that have split rank 4. And so they sit in this nice chain, these groups. And these are sort of the underlying groups for the sort of notion of modular forms on exceptional groups, these special automorphic forms. So all these groups in this chain have a sort of very similar structure at the real place. And so in particular, if you look at the maximal compact subgroup of the real points, it has a surjection to SU2 mod mu2. And G mod K for all of these groups does not have Hermitian structure. The symmetric space has no Hermitian structure. So now I can sort of define for you what these modular forms of on these groups G are. So I should mention that the idea here is that if you have a group that has Hermitian symmetric space, if G is a real group that has a Hermitian symmetric space, the maximal compact subgroup K has the property that it has a non-trivial surjection to U1, the smallest compact Lie group. And so the groups here are special in that they have the maximal compact subgroup has a surjection to the next smallest compact Lie group, SU2 mod mu2. Okay, so it's fixed an integer at least 1. Then a modular form on G of weight L is an automorphic form that's valued in the 2L symmetric power representation of the maximum compact subgroup K. So K maps to SU2, which then has a standard representation, and then you can take the 2L symmetric power. So you have an automorphic form that's valued in that representation of K that's equivariant, has an equivariant sort of action of the maximal compact subgroup K. So phi of GK is K inverse applied to phi of G for all of G in the group and K in the maximal compact subgroup. And moreover, you satisfy a special linear differential equation, DL of phi is identically 0. So this is supposed to be the analog of the Cauchy-Riemann equations. So this definition is due to Gross and Pollack and Gangros and Salem. It's a paraphrase of the definition. So here's a theorem that says that these modular forms have a robust Fourier expansion. So fix an integer L, then there's a Fourier expansion normalized over the integers that's compatible with pullbacks between these groups G. Okay, and so sometimes when I talk about this stuff, I end up talking about this theorem too here. But instead today, I'm gonna try to ask that you take it as a black box and discuss some applications. So what does the theorem mean? So it means you can, so given an automorphic form, given a modular form of weight L, so one of these special automorphic forms, you can ask the question, are all of the Fourier coefficients valued in some ring R contained in C? So that could be the integers, could be Q, could be Q bar, etc. And the Fourier expansion is robust and compatible with, it's compatible with pullbacks in the following sense. So if you take two groups, G1 and G2, sitting inside each other in this sequence, then you can start with an automorphic form, a modular form on one of the bigger groups, and pull it back to the smaller group, and it still will be a modular form of weight L. So it'll still satisfy the special differential equation. And moreover, the Fourier coefficients are sort of finite sums. The Fourier coefficients of the pullback are finite sums of the Fourier coefficients that you start with. So again, that's sort of a very special property of these modular forms. Usually if you take an automorphic form in some group and pull it back to a smaller group, you sort of would have no idea what the Fourier coefficients look like of what the Fourier expansion looks like of the pullback from the Fourier expansion that you started with on the bigger group. Okay, so the motivating question for me is once you have this sort of robust Fourier expansion, the motivating question is, does there exist a basis of modular forms on G of weight L for which all the Fourier coefficients are in Q bar? So if you have a group with Hermitian structure and you look at the holomorphic modular forms, then the analogous question is true, but the proof is sort of algebro-geometric in nature. And so here, there's no obvious algebraic geometry, but there's still this Fourier expansion. So this is, to me, the sort of the motivating question. Okay, so now I can get to the, I can take the main result that I want to talk about. So here's the theorem, and it's a combination of work of Wojtek Gahn, myself, and Gordon Savin, just sort of putting together various results of the three of us. And the proof I'll explain who does what here. So there's this square integrable automorphic forms, theta min and theta next to min on E8 with the following properties. So let P denote, so E8 has this group E7-3 sitting as a levy. So let the levy of a maximal parabolic subgroup. So that's important. So theta min is a weight 4 modular form with all Fourier coefficients in Z, and its constant term along this, the unipotent radical of this parabolic P is essentially Kim's weight 4 holomorphic modular form. And theta next to min is a weight 8 modular form with Fourier coefficients in Q, and its constant term along this, this maximal parabolic is essentially Kim's weight 8 modular form. And moreover, these modular forms are singular in the sense that many of their Fourier coefficients are 0. Okay. So the Fourier expansion is sort of, it's along the unipotent radical of this parabolic P. So denote that by N. And the Fourier coefficients, because you're taking the Fourier expansion along this unipotent radical, the Fourier coefficients are parametrized by elements of the dual of the abelianization of N. So this is some vector space, and it has a notion of rank, just sort of like the symmetric matrices have a notion of rank. And here the rank takes values in 0, 1, 2, 3, or 4, with 4 being the non-degenerate elements and the rank 0, 1, 2, 3 elements being the sort of degenerate ones. So these modular forms are singular in the sense that the Fourier coefficients of this minimal modular form are 0 unless the rank is 0 or 1, and the Fourier coefficients of this next to minimal modular form are 0 unless the rank is 0, 1, or 2. I have some remarks about the results. So the first remark is that Gross and Wallach constructed some small unitary representations of this real group E84 that are small in the sense of Gelfand-Kirchhoff dimension. And one should think of these automorphic forms theta min and theta next to min as globalizations. So in the case of theta min and this representation pi 4, that's true, and it's proved by Gahn and Savin, and it should be true, but it's not proved for this theta next to min. That should be a globalization of this small unitary representation pi 8. Another remark is that on the split group E8, there's analogs, and the analogs of these are sort of completely spherical automorphic forms, split E8, so even at the real place. And so the minimal automorphic form on split E8, this was constructed by Ginsburg, Rallis, and Sudri, and this next to minimal one was constructed by Green, Miller, and Van Hove, and Chubutaro and Chapa in the case of the next to minimal one. And it's also been recently studied by Gravich, Gustafsson, Kleinschmidt, Persson, and Sahi. And this is a very nice collaboration they did that. So, so where do these automorphic forms come from? How do you construct them? So they're constructed as special values of Eisenstein series associated to degenerate character, a character of this parabolic P. So Gahn constructed this theta min and proved that it's square interval constructed as a residue of an Eisenstein series. Okay, how does one prove this result? So for some notation, let G be this exceptional group E8 and P be the Heisenberg parabolic. So this is the maximal parabolic with E7, 3 as its levy. So you can take a character of the Heisenberg parabolic, call it nu. So this is nu is the notation for the generating character of this Heisenberg parabolic. And one constructs Eisenstein series associated to characters of nu. So so fix an even integer L, at least 1, and denote by this f of GLS, a section of this induced representation, the particular section, which is spherical at every finite place. And at the Archimedean place, it's a sort of a special sim to the 2L valued section. So then you can create an Eisenstein series out of this section. And if the real part of S is sufficiently large, then it converges absolutely. And there's a special point, which in this normalization is L plus 1. So L here is this sim to the 2L valued section. And so if you take S to be L plus 1, and that's in the range of absolute convergence, then you get one of these sort of special modular forms of weight L. So I have a question here, which I don't know the answer to, which is, do these modular forms have, these special Eisenstein series have rational Fourier coefficients? Okay, so that's in the range of absolute convergence, but to get these minimal modular form, this next minimal modular form, you take a point that's outside the range of absolute convergence. So fix L to be 8, so motivated by work of Gross and Wallach, and so then you look at this Eisenstein series that I've defined here. And it turns out to be regular at the special point S equals 9, even though that's outside the range of absolute convergence. And it defines a square interval weight 8 modular form at that point. So to prove that it's regular and square interval, that's just sort of a bunch of intertwining operator calculations. And then the fact that it's a modular form, saying that it's a modular form at that point means it satisfies some sort of special differential equation. So that's the definition of this theta next to min. And so now here comes Savin's result. So Savin analyzed the degenerate principal series corresponding at the finite places corresponding to this Eisenstein series. So he proves that the spherical constituent of this degenerate principal series is small in the sense that many twisted Jacquet modules are 0. So from Savin's result, you can conclude that this theta next to min has 0, rank 3, and rank 4 Fourier coefficients. So it's got this notion of Fourier coefficients because it satisfies a differential equation. And then Savin's result, the finite places, tells you that the rank 3 and rank 4 Fourier coefficients are 0. And so the result is that this weight 8 modular form has rational Fourier coefficients. So like I said, Savin's result gives the vanishing of the rank 3 and rank 4 Fourier coefficients, and some sort of explicit computation outside the range of absolute convergence gives the rationality of the rank 1 and rank 2 Fourier coefficients. And then the constant term is analyzed using work of Henry Kim. And so this is the last slide. So how does one prove that the Fourier coefficients, these rank 1 and rank 2 Fourier coefficients, are rational? What one does is, if you think of E84, and it has a D7 type levy, and what you can do is, so that D7 type levy is isogynous to SO311. So one can take the constant term of theta next to min down from E84 to this SO311, and one gets a sort of a special Eisenstein series on SO311, and one proves that these special Eisenstein series, they satisfy a differential equation, and they have some notion of Fourier coefficients because of that. And one proves that these special Eisenstein series has rational Fourier coefficients. And then one backtracks and can identify the Fourier coefficients of the rank 1 and rank 2 Fourier coefficients of this next to minimal modular form with the Fourier coefficients of this special Eisenstein series on SO311. And then finally, how does one get the rationality of these Fourier coefficients of these Eisenstein series on SO311? So it comes down to some explicit computation of a certain Archimedean Jacquet integral. So everything else is sort of easy, but one has to do this sort of explicit integral, and that's maybe the interesting part of that calculation. And I'll stop there.
Thank you. So if you can see everyone, they're clapping. So I'll open it up for questions. Okay, I'll go first.
Okay, go ahead.
Oh, Mutu, go ahead.
Hi, Aaron. Can you say a few words about, you had two theorems earlier, one of by Kim, and I forget the other theorem, but both the statements where the coefficients were integers. And then in your theorem, you proved rationality.
Right, so the
well, first my question
so the
is,
theorem on this theta next to min,
go about showing their integers, and
sorry, say again?
Idea?
Mutu, you have to ask your question again. It got garbled.
Well, I was wondering if you can say a few comments about how one goes about proving integrality of those coefficients. You prove rationality, and then in these theorems, Kim shows explicitly their integers. How does the proof work for a theorem?
Yeah, so it's so first of all, I should say that I should prove integrality, and it's just sort of by not doing enough work, I have the rationality as opposed to integrality. So it should be true that the Fourier coefficients are integers. And so the way one does it is all of these sort of special automorphic forms are defined as special values or residues of degenerate Eisenstein series, and the proof and the calculation of their Fourier coefficients is just sort of a explicit computation with the Eisenstein series.
Okay, and in your case, you reduce the calculation to an Eisenstein series on a different group?
Right, exactly.
Where you can calculate the coefficients.
Yeah, exactly, where one can calculate them more easily. Exactly.
Okay, thank you.
And so in theorem 2, where you say that the Fourier coefficients on the bigger group can be expressed as a finite sum on the smaller group, I think that's
so the Fourier coefficients of the pullback, so the one on the smaller group.
Yeah, that's the whole point. So how explicit are those finite sums, or is it just an abstract thing?
It's just an abstract property.
Oh, okay.
Yeah, it's just an abstract property. Maybe I should mention, just to give some sense of the sort of the rigidity imposed by this differential equation. So it's true that if you have a modular form of weight L, at least one on one of these groups G, one of these exceptional groups G, and it's bounded, then it's necessarily cuspidal. So that sort of follows from this explicit, follows from the theorem behind this theorem 2 here. So if you're bounded and satisfy this differential equation, then you're necessarily cuspidal and thus rapidly decreasing. Yeah.
Cool. Okay, so let's thank Aaron.
Well, I've one more question. Are these the eigenforms?
Yes. Yeah. So they're spherical at all the finite places.
Okay, so and all further questions can be asked after we thank Aaron again. So let's thank him now. Okay, so yes.